Hi students, in the second video for online lecture 13, we are now going to talk about one of the most difficult theoretical topics, and that is hybridization. So what is hybridization? Hybridization is the theoretical explanation of how we get our molecular geometries. This is going to mix different orbitals, in this case our s and p orbitals, in order to explain why we get the shapes that we do. So let's talk about what a hybrid orbital is. We are going to take our s and p orbitals, mix them mathematically, and produce new atomic orbitals. But let's talk about some of the rules that we need to have. The first rule is the number of hybrid orbitals is equal to the number of atomic orbitals mixed. So if you use 1s and 2p, you need to come up with 3 equivalent new hybrid orbitals. We do not want to lose any orbitals in the math. Finally, the type and shape of our hybrid orbitals is based on the type of the atomic orbital we mix. This is going to either be done by a picture representation or by using our electron diagram representation. So let's start with the basic fundamental theory that led to hybridization. We can call this our valence bond theory. Covalent bonds form when orbitals of 2 atoms overlap. The most important thing that we want to notice is that the overlap region, very much like a Venn diagram, must contain the pair of electrons being shared. The overlap comes from the mathematical wave functions being in phase. This means that we are able to add our 2 mathematical functions together and that they constructively interfere using our ideas back when we were talking of quantum mechanics. The important part of this is that the better the overlap of our orbitals and our electron density, the stronger the bond. So as we've seen through bond strength, if we are going to get more constructive interference, we are going to get a stronger bond and a better interaction. So how can we optimize this interaction? So let us go ahead and look at this idea. For our first one, opposing spins of bonding electrons. This means that even in our ideas of having overlapping orbitals, we need to have 2 electrons with opposite spins. So if we were to have 2 electrons, one from each one of our atoms, having parallel spins, upon the mathematical addition of our 2 orbitals, one of them is going to have to flip, and you see that here in our hydrogen fluoride molecule. Number 2 states, hybridization uses as few as orbitals as needed. If 2 atoms are attached, we only need 2 hybrid orbitals. We are going to hybridize only the orbitals that we need, and we will leave the unhybridized orbitals to possibly hold on to electrons or to do other things. Finally, for number 3, when we hybridize the atomic orbitals, these are going to be having different shapes. So as you can see by our examples here, we were not forced to hybridize because we could still get the molecular geometries that we would expect between 2 atoms. So this works out very well. The problem is, once we get to more complex molecules, the shapes don't match up with the theory. So let us go ahead and look at those ideas. The first one we'd like to talk about is the sp hybridization. That is going to be taking one of our s orbitals, signified here as a 2s orbital, and a 2p orbital. So notice that we are going to take one of each type of our atomic orbitals. This is where I'd like to talk about the benefit of our atomic orbitals. Our s orbital is symmetric. The electron density is going to be right around the entirety of our atom and has a uniform distance. We like having that. But notice our p orbital. It is slightly further out, but the important part is that it has direction. Directionality allows us to go and point those electrons in a certain direction. So what we're going to do is mathematically mix the 2s and the 2p. You see that done here in our electron diagram. What will happen and result is a set of orbitals that is going to have energy in the middle of those 2 orbitals, and you see them here as our sp hybrid orbitals. What do those sp orbitals look like? Well, notice that it looks like a mathematical addition of the two electron densities together. For this sp orbital, you can see the left electron density with the left lobe, while we are going to have a small right lobe because of interference and the subtraction of our electron density. For our other sp orbital, notice that I have the right electron density, this addition of this lobe and this side of our s orbital, and then we would have a small negative lobe on the other side. But when we actually put them together in a molecule, notice that we have now taken the best parts of two orbitals, the symmetry of our s orbital, and now given it directionality and put it along the axis. And you can now see that with a simplified view here of our new orbitals. This is what gives us the 180 degrees that we are expecting for our molecular geometry. The reason that this is important is that if I were to go and use just the non-hybridized orbitals here, or I would go and look at my 2s orbital here, none of our bonding would make sense. First off, these are paired electrons. Why would paired electrons want to bond? They don't. But now if I put them in their own separate hybridized orbitals, you can now see here that they are willing to bond as unpaired electrons. So now let's go ahead and talk about the problem of the p orbitals. Remember, these are along the coordinate plane and at 90 degrees. Why would we result with a 180 degree bond angle if everything is at 90 degrees? So while this may be theory and a very rough explanation, hybridization is what gives us the degrees and shapes that we're expecting. At the bottom, you can see some colored beakers. This was a visual demonstration done in the late 80s and early 90s to help you understand what they typically call orbital contribution. Let's say that our yellow one is going to be our s orbital. Our blue one is going to be the 1p orbital we're going to use. And as you can see, once we mix them, we get a fairly good green color. This is because our hybrid orbitals are really 50% s orbital and 50% p orbitals. They have equal contribution, so they are going to have equal characteristics that you see there of the symmetry and the direction. Let's go ahead and see what happens if we add more p orbitals. So when we get to our sp hybridization, this is a very easy systematic explanation. We are going to take atomic orbitals that are dissimilar, our 2s and our 2p. We are going to mix them, and you can see our hybrid orbitals at the bottom, and we are left with two unhybridized orbitals. That is because we do not need to have more orbitals hybridized if they are not going to bind. So now you can see what it looks like for our sp hybrid bonding. We've taken our beryllium, we have done the hybridization, and you will see those hybrid orbitals here located in blue, and now they are able to bind to this chlorine atoms much easier because they have unpaired electrons ready to fill and occupy those locations. Because those hybrid orbitals are large and have unpaired electrons, they want to get as far away from each other as they physically can. You see those here at 180 degrees, and this matches up to the Vespers theory that we were seeing before. For our sp2, we are now going to have to add a second p orbital. So as you can see here, we have our atomic orbitals. And notice that for our boron, we would have two paired electrons here in our 2s, while you would only have one electron in the 2p. So it makes it seem like there would only be one bond that would want to happen. But if we hybridize the orbitals, now notice that upon the mixing and getting three sp2 orbitals, that we now get three electrons, one each of our hybrid orbitals. This allows our fluorine to bond, and this is how we would get the trigonal planar molecular geometry. So now with our color test, if I have my S as yellow, but notice that I am adding more P character into this, let's look at the resulting color of our final orbitals. This is much more blue than what we had previously. This is because our P character has increased. So now when we think of our hybrid orbitals, this is going to be 33% S and really about 67% P. This means that we're going to have more directionality, and our hybrid orbitals for the sp2 are going to look more P-shaped than they would S-shaped, and you can see that in our diagram. Finally, let's get to the holy grail of our hybrid orbitals, and that is the sp3 hybrid orbitals. Originally, when we were talking about the idea of methane, this was the molecule that had so many issues in explanation. Using the atomic orbitals you see here, if I were to go and do methane, there were many people that said, okay, I will be able to do 2 bonds because of the 2 lone electrons in the 2p orbital. When they started to figure out how many hydrogens were involved, they actually found out that it was CH4. So this could not have been the molecule. So then they looked at the atomic orbitals and said, okay, if that is the case, you would expect 2 hydrogens to be much longer because of being a part of the p orbital and having 2 hydrogens that are much shorter coming from our 2 s orbitals. The interesting part is that is not the shape either. In this case, you are going to get 4 hydrogens located around our carbon, all at equivalent distances and at the bond angle of the tetrahedron, which is 109.5. Nowhere in our atomic orbitals does that bond angle show up. That is because upon hybridization, you now get 4 equivalent orbitals that all want their optimized space, and this is how we result to the sp3 hybrid geometry. So while our standard VSEPR theory really can predict so many wonderful things, it is very limited based off of 90-degree bond angles and of the such. Once we get to the different bond angles of 109.5, this is the best explanation for the possibility of hybridization and mixing in equivalent orbitals to give us unpaired electrons that want to bind to other things. The nice part about it is that we can also go ahead and put lone pairs in our hybrid orbitals if need be. So notice that in my isolated nitrogen atom, I have a total of 5 valence electrons. If I were to go and hybridize, I can put those 5 valence electrons in 4 hybrid orbitals. In one of those hybrid orbitals, we are going to have a paired up electron set. This is going to be my lone pair, while I am able to go and form 3 outside bonds with my sp3 hybrid orbitals that have unpaired electrons. This is how you end up getting NH3 with a lone pair on our central nitrogen. We can also do the same for our oxygen. Notice that our oxygen has 6 valence electrons, and when we hybridize and go to sp3, here are our 2 lone pairs that we see historically on our water. Then we are able to take our 2 other hybrid orbitals and bind them to hydrogen, and that is how you get H2O. It should be well stated that the hybridization of atoms occurs greatly with our smaller atoms. As an atom gets bigger, historically, it doesn't have to hybridize as much because the volume gets bigger. So you're going to see a lot of hybridization for the atoms of boron, carbon, nitrogen, and oxygen. It will also happen with sulfur, phosphorus, and some other ones, but those are the main species we have to look for. So let's go ahead and work on this example. What is the hybridization of all atoms in the following molecule? So the first thing we need to do is go and draw acetone. So I have methyl groups coming off of a carbon, which is actually doubly bound to a oxygen. And we have the other methyl group on the other side, each one of the methyl groups having 3 hydrogens. So let us go and systematically talk about what we need to do. So the nice part about it is that hydrogen does not hybridize because it has only 1 electron and can stay in its atomic orbital. So we really have 4 atoms that we need to deal with, those being the 3 carbons and finally the oxygen. So let's go ahead and look at the left carbon. It has 4 attachments, 3 hydrogens and the carbon that is attached on the other side. 4 attachments means that I need 4 hybrid orbitals. So if I need 4 hybrid orbitals, I need to go and use 1s, and I need to get as many p orbitals as I need, and I will add that together and get sp3. So the nice part about it is that our left carbon is going to be sp3, and so will the right carbon because it is structurally equivalent. So these 2 species here are both sp3. Let us go ahead and look at our middle carbon. Notice that it has only 3 attachments. 3 attachments means that I need to have 3 hybrid orbitals. So in this case, 3 hybrid orbitals means that I need to have an s, and I only need 2 p's, and this means it's going to have an sp2 hybridization. So our carbon here in the middle is going to have sp2 in order to get those 3 orbitals. In the case of oxygen, notice that I have 3 attachments, one of them being a double bond and 2 pairs of electrons. This means that this will be sp2 as well. So let's go ahead and look at example B. For this case, we are going to have our carbon dioxide. So we have our carbon attached to 2 oxygens pulling in opposite and equal directions. So let's talk about the central carbon. It has only 2 attachments. So in this case, if I have 2 attachments, I need 2 hybrid orbitals. So that means that I need an s and only 1 p. So this is going to be sp hybrid. So our carbon is going to be sp hybrid in this molecule. If you look at our oxygens, they are structurally equivalent to our oxygen over here in our acetone group. So both of our oxygens are going to be sp2 hybrid as well. Make sure that you are working trying to understand the ideas of what atoms have historically what types of hybridization. But it's best to find the number of attachments and then determine the hybridization. So let's try this set of examples. What is the hybridization of the central atom of the following molecules? So let us go ahead and start with our chlorate anion. In this case, I'm going to have my chlorine in the middle, surrounded by 3 oxygens. So if I look at this, I should have a total of 26 electrons. So I will put my lone pairs around the oxygens. And then finally, I am going to have a pair of electrons on my chlorine. And in this case, you will notice that I have 4 attachments. 4 attachments being 3 oxygens bound to the chlorine, and then 1 lone pair. This is going to be an sp3 hybridized central atom. If I go ahead and look at my silicon tetrahydride, what I can do in this case is take my silicon, surround it by our hydrogen atoms, and notice that I have 4 equivalent attachments pulling in opposite and equal directions. Those 4 attachments mean that I need to have 4 equivalent orbitals. So in this case, this is going to be sp3 as well. So finally, we are now going down to our nitrite anion. So in this case, I will have my oxygen bound to a nitrogen and bound to the other oxygen. Remember that we must take that -1 charge to get the total number of electrons. And if I do this correctly, you will see that I will get a double bond between our oxygen and nitrogen here. and my nitrogen will have a total of 3 attachments, all of them being different. 1 single bond, 1 double bond, and 1 lone pair. However, we just want to know the number of attachments. In this case, there are 3 attachments, so this means it is going to be sp2 hybridized. For our last example, in example 7.7, we are now going to go and do our HCN. So we have our H bound to our C and bound to our N. So in this case, we are going to look for a total number of electrons to be 10. If we do that, we will get a triple bond here with a pair of electrons on the nitrogen. Now, what is the hybridization of our central atom? We have 2 attachments. Those 2 attachments being 1 hydrogen and 1 nitrogen. So if it's 2 attachments, I need 2 hybrid orbitals. So that is going to be sp hybridized. We will talk about the importance of this hybridization when dealing with our multiple bonds in our next video. So now let's go ahead and look at this example. Cysteine is one of 20 natural amino acids, and it contains atoms with different hybridization. Using the structure for cysteine, give the hybridization for all labeled atoms. First thing we want to do is look at our carbon A. Notice that he has 3 attachments: the doubly bound oxygen, our OH group to the right, and the carbon going to the left. So 3 attachments means that this must be sp2 hybridized. If we look at our carbon labeled B, you will see that he has 4 attachments: the carbon to the right, the hydrogen to the top, the amine group to the left, and finally our long chain to the bottom. So now having 4 attachments means that this carbon is going to be sp3 hybridized. So notice how I have adjacent carbons having different hybridization based off the number of attachments to those specific central atoms. So if we look at our answers, you're going to see that the correct answer for this example is going to be letter B. So as you can see, there is a great importance when it comes to our S and P atomic orbitals being used to create our hybrid orbitals. There's a big issue though. Back in the day when they were doing this, they started to discuss the possibilities of the extended valent molecules. So what would happen is that they would say that we are going to go into the D block and produce 5 hybrid orbitals, going and getting one of my D orbitals and producing the sp3d hybridized geometries. However, this is not true. This was a misnomer, and even though I am bringing it up here, many general chemistry textbooks still use it, even though it is incorrect. The correct bonding structure will be discussed in great detail if you are to go and take inorganic chemistry and use the ideas of 4-electron 2-center bonding, or what is typically called 4-electron 3-center bonding. So you're going to run into many different problem types in which they will say sp3d hybridization, 4 and 5 attachment species, but that is actually not going to be consistent when you get to higher chemistries. This is also true for the 6 attachment species of the octahedron molecular geometry. This was incorrect when they believed that this was sp3d2, because the idea of all of this is if you're going to go and use 2 of the d orbitals, what is stopping you from using 3, 4, or all 5? Why can you not go out and have 8 attachments to an atom? So the issue in all of this is that when we were starting to build all of our molecules, the limitation of only using 2 orbitals didn't seem to make sense as we were going along and doing this type of work. So if you run into problems with the extended valence, you can use the sp3d2, but know that it is not going to hold up when you get to further chemistries. So here is a summary of the various hybrid orbitals that you're going to use. So remember that if you have 1s and 1p, you get the sp hybrid, and it is going to form the line. If we go to the trigonal planar and use the 1s and 2p's, you would get a total of 3 total orbitals and have the sp2. If you go to 1s and you use 3p, you'll get the 4 sp3, and so on and so forth. So this is the explanation on how we get the molecular geometries. This is all theoretical and helps explain what you need. If interested, go to the PowerPoint slides and click on the link, and you will see how the mathematical construction happens using one of our textbook resources. In this video, you saw how we are taking atomic orbitals, mixing them up even though they are inequivalent, and helping us produce the molecular geometries that you have seen lectures prior. In our next video, we're going to talk about the importance of these types of orbitals, as well as what we call our binding modes and how our bonds are formed. Have a great day.